Assalamu alaikum, we are Team Grilled Chicken, and this is the official video submission of our EEE 430 Digital Electronics Lab project on Digital Snake Ladder game. Through this presentation, we aim to provide insightful information and a clear understanding of our Snake Ladder game, how the game works, and how each module present in this project functions. We hope you find it engaging and informative. Our team consists of 7 members. Each of us has contributed to different criteria to bring this project together. So without further delay, let's begin.
You're required to construct the digital version of a snake ladder game for 2 players. This game will be played on a 4x4 LED grid board that represents the positions of 2 players ranging from 0 to 15. In each block, there are 4 LEDs of different colors. The LED in the bottom left indicates player 1's position, while the LED in the bottom right indicates player 2's position. The LED in the top left marks the presence of a snake on that block, while the LED in the top right marks the presence of a ladder on that block. We are using a user-defined input system for the snake head, snake length, ladder bottom, and lastly the ladder length. We are going to illustrate how we are doing so later in the video. This essentially means that on the board, 2 ladder LEDs and 2 snake LEDs will always be turned on to indicate their positions and presence. The player's LEDs will turn on based on their updated positions after dice rolls. We will always be able to keep track of the players this way visually and know who is in the lead. A player will win only if they reach 15 before the other player. We are now moving on to our board module. For the main module of the game, we created 16 4x4 grids, where in each grid we placed 4 common cathode LEDs representing 4 different colors: red for player 1, blue for player 2, yellow for the snake, and green for the ladder. Each LED has been connected to a 200 ohm resistor. This has been done in order to limit the current flow through the LEDs so that they are not damaged when they are used physically during hardware implementation. Now all the LEDs are in active low state. We did this by connecting all the positive sides and providing them with power by setting up common wires among them, which indicate that they are activated when their logical output will be 0.
Let us understand how the dice in our Snake Ladder game works. First, we constructed a 555 timer IC, which serves as our clock pulse. In the dice module, we have given an AND gate, which has one input as the clock pulse of our 555 timer IC, while the other input is to be determined by an SR latch. And in the SR latch, one input is given as ground when taken through the NAND gate present in the bottom, while the other is powered. But when we used the push switch present here, we make both of our inputs ground, thus giving us the logical 1 in the AND gate. So, whenever the push switch is pressed, the SR latch gives us the value 1, and then the AND gate passes the clock pulse, which is then supplied in the later parts of our module. When the push button is turned off, the circuits get opened and AND gate receives 0 and doesn't allow the clock pulse to pass through the later parts of our circuit. The clock pulse is entered in the first D flip-flop, which gives the Q output logical 1 in every 2 pulse, serving as least significant bit. And another D flip-flop does the same thing, taking clock pulse from the Q prime of the first D flip-flop, serving as the most significant bit, thus giving us a smooth 2-bit up counter ranging from 00 to 11. The number is then taken to a decoder, which is connected to a 7-segment display in order to see the value. We know that we have gotten a number between 1, 2, or 3, so the 3rd and 4th bits in the decoder are not required, so we have only used 1 and 2 inputs in the decoder, and the other 2 are taken as ground. So, when we get the output, a fair value is seen in the 7-segment display. So, whenever the push switch is turned on, we get a clock pulse, and a combination of D flip-flops acts as conventional up counter, giving us a value which is then passed through to show in the 7-segment display. And this is the value we get from the dice.
In the case of the ladder decoder, there are 8 inputs and 16 outputs. Each of the outputs go to each of the LEDs of the corresponding number. For example, in case of ladder, LED 0 goes to the 0 number LED, LED 1 goes to the LED number 1, and vice versa. So total 16 outputs go to 16 LEDs. We mentioned that our circuits is based on active low state, and we also learned that for the ladder only 2 LEDs will stay on. So among these 16 outputs, 2 are delivered as 0 and other 14 are delivered as active ones. So how do we get those 2 values? First of all, we need to understand what those 2 values mean. Those 2 values are explaining the position of ladder bottom and ladder top. But in the case of inputs, we can see a total number of 8 inputs, 4 of which are selected as ladder bottom and 4 of which as ladder length. We have taken these 8 as input variables because as per our instruction, the ladder bottom and ladder length was to be defined by the user. We also mentioned before that, the outputs which will supply as active 0 are ladder bottom and ladder top, not ladder length. So we somehow have to do a calculation where the output will include a ladder head, which will obviously be the sum of ladder bottom and ladder length, and this calculation is done in the child sheet of the ladder. Inside the ladder decoder module, we can first see an adder, and as mentioned, the adder gives the sum of length and bottom as top, which is the desired output. And then we include the ladder bottom and ladder top into two decoders. These two decoders convert this 4-bit binary number to the corresponding output. The bottom one gives corresponding output of the bottom input, and the top gives the corresponding output of the top input. And we can see that the outputs are passed through NOT gate. That is why when the input is 1, we get the 0 as output. So now from the ladder bottom decoder, we get only 1 0. We should have got only 1 1. But as the outputs are passed through NOT gate, we get only 1 0. And from the ladder top decoder, we also get 1 0. And in the next part, we can see that the output number 1 from the ladder bottom and the output number 1 in ladder top, they are both together taken in an AND gate. The output number 2 from both decoders are also taken in an AND gate. So total 32 outputs are taken in AND gates. We know that the ladder bottom and ladder top are not the same number because we have ladder length as a value. If ladder length was to be 0, then the ladder bottom and ladder top would have given the same output signal. So as ladder length has a value and ladder bottom and ladder top are different, so among the 16 AND gates, 0 is supplied in one of the inputs of each two gates. All the other 14 AND gates get 1 as inputs. So when the complete calculation is done, then only 2 of the AND gates give a 0 value, while the other 14 gives us 1. This is our desired output, because in the parent sheet of the ladder decoder module, we wanted 2 0 signals and 14 1 signals, and those 2 0 signals are our desired active low state signals, which will be displayed on board. Now in the second decoder, which is the snake decoder module, we see almost the exact same things. The only difference is here we didn't add the snake length with the snake head. Rather, we subtracted the ladder snake length from the snake head using 2's complement, because this is how the snake functions, and this is what we were supposed to take as a user input. After that, it follows almost the same formula where the ladder subtractor gives us a required value, which is the snake tail, and the snake head is taken from before the before input of the snake head, and these two decoders supply 0 values, which are then ANDed, and which gives 14 ones and 2 R0, which are our desired outputs. The third and fourth decoder are our player 1 and player 2, which are player position decoders. These player position decoders serve exactly as our snake and ladder decoders, but it is a lot simpler. It serves the position of player directly. So among these 16 outputs, only one is 0, which turns on the LEDs. These inputs are taken from a memory module which fixes the position of the player after each dice roll or run.
Now, from the basic snake and ladder game, we know when a player falls in a ladder bottom, he gets promoted to ladder top, and when he gets into snake head, he gets demoted to snake tail. How is this logic incorporated? This logic is incorporated in the snake ladder logic module. Here we get the old position from a player and compare it with the ladder bottom or snake head. If the old position is the same as ladder bottom, then he gets promoted. And if the old position is the same as snake head, then he gets demoted. And after that, the old position becomes a new position. So if any promotion or any demotion has not happened, then the new position is the same as the old position. The old position gets checked every time a dice roll has happened. So the old position adds up with the dice and then checks with ladder bottom and snake head, and then determines whether the new position is the same or different. inside the child sheet, we first see that the old position is added with the dice value. So we got the number which we will compare. Now, in the comparator, one is obviously the old position, the other is the ladder bottom. So, when we get the ladder bottom, the same as the old position, we know the ladder length needs to be added to the old position. So, we use an adder where one input is taken as the old position, the other will be taken from the AND gates only when ladder bottom and old position are equal. From this comparator, we get the output 6 as 1. And this output 6 is shorted with all the AND gates, and the other inputs of the AND gates are taken as ladder lengths. So only when output number 6 of the comparator is 1, the ladder length gets passed from the AND gates and it gets added with the old position. But when the old position and the ladder bottom are not equal, then comparator output 6 supplies 0, and the AND gate doesn't let the ladder length pass. So from the ladder length 0 gets added, so we get the old position. The same logic is applied in the snake head also. Here the old position gets compared with the snake head, and if the snake head and the old position are equal, then we subtract the snake length from the old position and give the output as the new position. Here we use 2's complement method to subtract the length of the snake in an adder. And here we also took the snake length through an AND gate where the comparator compares with the snake head to give the final position, which is the new position, after the ladder calculation and compares it. This is how our snake ladder logic module calculates the old position and the newest position with the snake head and ladder bottom.
So far, we have discussed many aspects of the system, but there are still some unaddressed issues. One of these is how each player switches turns, and another is how the system keeps track of the player's previous position, given that we are only inputting the snake and ladder values directly. These tasks are primarily handled by the memory module. In the main system, the key inputs are the new positions, which are stored in memory, while the previous positions, which are retrieved from memory, are sent to the snake and ladder logic module. Additionally, the player position decoder, which determines player placement on the board, relies on this memory. The memory module is responsible for managing the next turn order, deciding which player moves next, and ensuring that the correct position updates are applied. It also handles the game reset, which can reset the game at any moment, either after winning or any other time, and the player selection by showing which player's turn it is by lighting the same color LED as the player color. In the middle of the memory module child sheet, we can see similar structures on both the upper and the lower side. Each of these is built using 4 D flip-flops. Since a single D flip-flop stores 1 bit of data, each of these store 4-bit data and hence a position value. If both the upper and the lower sets of D flip-flops were to operate simultaneously, a new position would be then stored in both sets at the same time. These stored positions would then be used to activate the decoders and then the board module's LEDs displaying the player's locations. However, as the game is, we do not take inputs at the same time because the players don't take turns at the same time, so we do not receive the position updates at the same time. To handle this issue, a NOT gate is used alongside an AND operation on the outputs of the two sets of 4 D flip-flops. The outputs of each set pass through 4 AND gates, and then the player's selector input determines which of these sets are active. When the player selector input is 1, only one of the 4 outputs is passed through while the other set is forced to 0. And since one set outputs a value while the other outputs 0, an OR gate is used to ensure that only the active player's position is processed. After each turn, the player selector module toggles between 0 and 1, ensuring that only one set, either the upper one or the lower one, is activated per turn. And as for how the player selector module switches between 0 and 1, we will show you that by referring back to the main sheet. Here we have a JK flip-flop. We know for a JK flip-flop, if both the inputs are set active, in this case high, the JK flip-flop will toggle its output. If the output is 0, it will become 1, and if it's 1, it will become 0. So we have given active high to both the inputs, and then for the clock pulse we have taken the selector output from the memory module and passed it through a NOT gate. What will happen now is that each time the selector output gives us a pulse, the output of the JK flip-flop will toggle. And what will happen now is the outputs light one of the two LEDs here. These LEDs are representative of the players on the board. So when the red LED lights, it's the red player's turn, which is player 1, and blue for player 2. And when one LED is activated, the corresponding player selector output is generated. Then this output is ANDed with both sets of D flip-flops in the center of the memory module, ensuring that only the active player's position is updated. The reset module has a fairly simple construction compared to the other ones. It consists of a push-up switch connected to power and here passed through a NOT gate. When the switch is turned on, the NOT gate outputs a logical 0, which is then sent to the reset pin. This reset signal is applied to all the reset positions of the D flip-flop sets, clearing the stored values. Additionally, the reset module has another NOT gate output that is connected to the reset input of the toggling JK flip-flop used in the player selector module. This ensures that both the D flip-flops and that JK flip-flop in the player selection process are properly reset when needed. And in the memory module, we also see inputs for a clock pulse and a dice value. The clock pulse functions as a standard clock signal within the circuit, nothing more. The dice value is passed through latches and D flip-flops, storing and supplying the dice result to the D flip-flop sets. And finally, since the player selector output determines which D flip-flop set is active, it ensures that the dice value is stored only in the correct set, allowing the game to alternate turns properly.
Next up, we have the winner module. This module is very simple. Essentially, it uses a comparator to compare the current positions of the players with a pre-given value in the comparator. So as you can notice, we have already input 15 in the comparator, and it is going to be compared with each respective current positions of the players. Whenever a player has reached the position 15, the comparator will send an active high signal through its sixth output, and that will indicate that the game is over and that particular player has won the game. We were also required to insert a bonus condition in this project where we were told that if a player needs precisely 1 or 2 in order to win this game but receives more than that value, then that player will not progress. So for example, if someone is on position 14 and they roll 2, then they will still be stuck on position 14 and the game will alternate to the next player. This is accomplished through the carryout operation in the snake ladder logic module. We can see that when an old position and the dice add up to make the new position in the first adder of the snake ladder logic module, we get a carryout. This carryout will only become 1 when the total sum of old position and dice exceeds 15. Otherwise, in majority of cases, the carryout will always be 0. So whenever the carryout is 0, which is majority of the times, we can see that just beside the D flip-flop sets, we have AND gates, and there the carryout is passed through NOT gates as one of the 3 inputs of the AND gates. This is how carryout always gives 1 to the AND gates as it is 0. So therefore the output of AND gates become normal and the D flip-flops can continue their operation. But only when the new position of the player exceeds 15 after summation, the carryout becomes 1. So therefore, after proceeding to the NOT gates, they deliver 0 to the AND gates, as a result of which, regardless of whatever the old value is, the D flip-flops never update the value to the current position. So the player essentially does not progress. However, the player switching operation occurs normally, as the carryout is not connected with the player selector module.
Until now, we have discussed all the present modules of our project, how they function and how they are interconnected. In this final part, I am going to play the game once to clear out all things. First of all, we will select the values of ladder bottom and ladder length, as it was supposed to be taken as user input. Suppose we have taken ladder bottom as 3 and ladder length as 3 also. Now, as per our previous explanation, we said that ladder bottom and ladder length will be summed up to get the ladder top, and only the LEDs designated for ladder bottom and ladder top will be lit up in the board module. We can see in the board module that the designated LEDs number 3 and number 6 for the ladder are lit up. In case of the snake, we have given the values of snake head as 7 and snake length as 3. So after subtracting, we get the snake bottom as 4. And in the board module, we can see that LED number 7 and LED number 4 designated for snake top and snake bottom are on. Now, we're going to check whether our snake and ladder are working or not. And in order to do that, we will put the players in snake head and ladder bottom and see if they are demoted or promoted. To get such specific values in players, we have to control our dice. So we can select which output we should take, and in order to do that, first we are going to set the capacitor C2 of our 555 timer IC to 4 microfarads. This will slow down the process of clock pulse. First one is for player 1, so in the top left in the player selector module, we can see that the LED of player 1 is lit up. After reducing the capacitance, by pressing the push switch, we can see that the dice is rolling very slowly and we can actually see each value separately. Player 1 is in position 0 and the dice bottom and the ladder bottom is in position 3. So, if we give 3 to player 1, he will be promoted directly to position number 6 by using the ladder. So after giving 3 to player 1, we can see that he has been directly promoted to position 6. By this time, in the player pose selected module, the LED is changed to player 2. Now, let us give player 2 a value of 2. A value of 2 is given. We can see that if player 1 gets a value of 1, he will reach the snake head and get demoted to snake tail, which is position number 4. So let us try that. We can see that by giving 1, we can easily achieve that. We can come to the conclusion that our snake and ladder works perfectly. Now let us reset the game by pressing the reset module. We can see that the game has been reset and the players are again in 0 position. Now let us revert back our dice to faster mode and play the full game. We can see that player 1 has won the game, and in the winning module, the LED for player 1 is turned on. We have also created printed circuit boards or PCBs for all the modules of our project. The images of the PCBs and how they are interconnected is shown.
That wraps up our demonstration of the snake and ladder game, built using Proteus. We have explored how the dice roll mechanism works, how player movement is tracked, and how the game logic brings the classic board game to life in a digital simulation. We hope you found this demonstration insightful. Jazakallah khairan. Thank you for watching.